Digital systems process information using combinational logic. In these circuits, the output is strictly and instantly determined by whatever inputs are present at that exact moment. The moment those inputs change or disappear, the output changes with them. A combinational circuit has zero internal capacity to hold a state. It calculates but cannot remember. To build a system that retains data, we use sequential logic. Looking at this diagram, the top section shows the standard combinational signal flowing from left to right, from inputs to outputs. The path returning from the memory elements back into the combinational circuit allows the circuit's past behavior to directly influence its present state. Digital memory functions as an active, continuously looping physical feedback circuit. Routing a signal back on itself introduces a severe physical risk. Unregulated feedback loops are inherently unstable and can easily oscillate out of control. To engineer a reliable system, we have to build a synchronized 1-bit memory cell from scratch, systematically solving the physical hardware constraints that cause those instabilities. We will trace this evolution from the raw SA latch through the corrective D latch and finally the edge-triggered flip-flop. These evolutionary steps address the specific physical timing flaws that would otherwise make high-speed computation impossible. This diagram shows the SR latch. Cross-coupling two NOR gates creates a bistable circuit. Looking at the top row, when set receives a 1, the circuit routes that signal, forcing Q to hold a 1. The latch is now set. By design, the secondary output, labeled Q', is the strict inverse of Q. If Q is 1, Q' must be 0. To clear the memory, look at the third row. Sending a 1 to reset forces the Q output to 0, but a vulnerability exists below. If both set and reset receive a 1 simultaneously, both NOR gates output a 0. This means Q and Q' both equal 0. When inputs are removed, the gates race to recover, throwing the circuit into an undefined state. While the SR latch successfully creates memory, its reliance on external signals to avoid this input state makes it unsuitable for automated computing. We have to physically alter the circuit so that the set and reset pins can never receive a 1 simultaneously, regardless of external errors. This diagram shows the D latch. We replace independent inputs with a single data line. One path runs through an inverter, guaranteeing complementary inputs. Checking the table, a 1 forces the output to 1, a 0 forces it back to 0. Adding an inverter creates a hardware constraint that prevents the undefined state from occurring. Even with a stable latch, CPUs have millions of gates. To coordinate data, the system requires a master clock to synchronize operations. We add a control input to the latch. This acts as a gatekeeper, determining exactly when the latch is permitted to accept new data. This timing diagram shows a vulnerability. In wave A, the latch accepts data continuously while the clock pulse remains high. For the full length of that plateau, the latch is transparent to the data line. If the data signal fluctuates while the clock is held high, the latch doesn't just hold the intended value, its output mirrors the noise. Level-sensitive latches create race conditions. To ensure reliability, memory must be locked down to a fraction of a nanosecond, immune to mid-cycle voltage spikes. This upward arrow illustrates the solution: edge triggering. The circuit is designed to sample data only at the exact moment the clock voltage transitions from low to high. Instead of a vulnerable plateau, the data window is narrowed to a microscopic slice of time. We use the master-slave D flip-flop, two latches separated by a clock inverter. When the clock is low, the master reads data while the slave is disabled. When the clock shifts high, the master locks and the slave wakes up to push data outward. This alternating isolation creates a flip-flop. Because the input and output are never physically connected simultaneously, the cell is immune to mid-cycle timing glitches. This graphic symbol represents our finalized D-type positive edge-triggered memory block. The triangle on the clock input signifies the edge-triggering architecture operating inside. More complex memory units are built by taking this reliable D flip-flop and wrapping it in additional combinational logic. In the circuit diagram for the JK flip-flop, the advanced capabilities to set, reset, or toggle are achieved by surrounding a standard D flip-flop with external feedback gates. Whether engineering simple counters or gigabytes of RAM, the foundational bedrock remains this edge-triggered memory cell. The path to reliable memory moved from the unstable SR latch through the logic constraints of the D latch to the isolation achieved by the master-slave flip-flop. Building a processor means solving the physical reality of electrical timing constraints and voltage noise. Modern computation relies on precise synchronization, achieved by locking the flow of memory to the microscopic edge of a ticking clock.